Alright, today we're going to go ahead and talk about stress, strain, and elasticity. But before I forget, I want to let you know that on the next class day that I see you, we will have a vocabulary quiz over these terms and definitions that I've introduced you to today. I will go through the terms very quickly, so if you still need time to write them down, just let Mr. O'Keefe know and he'll pause the video. So that way you'll have enough time to write down the definition. So always, if you need to, pause it and then he can click play again so we can continue with the rest of the slides. Alright, so let's go ahead and start. So remember, for your class, your quiz would be on Tuesday. So we'll do a little brief review, very simple quiz, vocab quiz. We'll go over the terms again, answer any questions or concerns that you may have, and then we'll take that quiz at the end on Tuesday. So let's go ahead and start with the first vocabulary term, which is stress. Stress is the force per unit area on a surface within an object, and it's represented by the Greek letter sigma, and it refers to the internal forces acting inside of an object. So I've given you the equation here for stress, and it's, again, sigma equals F over A, or in other words, the F represents the average force and the A represents the cross-sectional area of whatever object it is that you are interested in. The main thing that I want you to get from this vocabulary term is this first part, the force per unit area on a surface within an object. And I also want you to remember that the symbol that we use to represent stress is the Greek letter sigma. There are three types of stress. This is very important. You will have to remember this. The three types of stress are compression force, which is the pushing force perpendicular to the surface, tension force, which is the pulling force perpendicular to the surface, and then shear stress is the last type of stress, and that's the pushing force in the same plane as the surface. So I'll give you a few examples of each of these, the first one being compression force. A compression force, once again, is a pushing force that tends to shorten objects. Compression. Okay, so it's pretty obvious. Most of us know what the word compression means. And I'll give you an example. These are two examples of something that is being compressed. So basically, here you have a force that's pushing downwards, and here you kind of have a force that is pushing upwards. So eventually, when you compress those two, the elastic material will essentially bust or burst. This kind of looks like a balloon to me. So in a way, it's kind of like you're bursting the balloon. It'll pop. Same thing with something that's a rigid material. So this concrete block, if you compress it, essentially it'll break or it'll shatter. Those are examples of compression. Tension is a pulling or stretching force that tends to lengthen objects, and the most popular type of tension that a lot of us use as an example is tug of war. So when you have two teams pulling on a rope, that creates a tension force between that rope. And the next type of stress, which we really won't get into, is shear stress. And an example of that are a pair of scissors and its blades. Those are examples. Scissors are example of shear stress. Strain is the change in the dimensions of an object caused by the stress that the object is under. It is dimensionless, and in another term that engineers may use will be deformation. So basically, if you think about it, strain is really looking at the object once stress has been applied to it. So it kind of makes sense why the equation right here is the way that it is. We use this Greek letter for strain, and we call that epsilon, E-P-S-I-L-O-N, epsilon. So you may want to remember that. We use the Greek letter epsilon for strain. And it's delta L over L naught. So in other words, it's the change in length over the original length. So if you think about it, it kind of makes sense with the definition, because it's looking at an object once stress has been applied to it, and looking at its original length versus the length once the stress has been applied to it. So in other words, the deformation part of it. So just remember that part for strain. The change in the dimensions of an object caused by stress that the object is under, and then remember that it's represented by the Greek letter epsilon. The next vocabulary term is elastic deformation, and that's when an object returns to its original shape after a force is removed. And it's also the linear part of a stress-strain curve. So remember that part. And we'll look at a stress-strain curve in a minute. So basically, I've given you an example of a rubber band. When you basically apply force on that rubber band, just kind of play with it a little bit. When you remove the force, in other words, your fingers stop playing with it, the rubber band returns back to its original shape. So that's an example of elastic deformation. The next type of deformation that there is plastic deformation. And that is when an object does not return to its original shape after a force is removed. That should be is. And it in a stress-strain curve, that is the non-linear part. So for example, I've given you, or I've stated that a paper clip is an example of plastic deformation. So whenever I kind of bend the paper clip, okay, or I kind of start unbending it, it's not going to return back to its original shape of being a paper clip because of the material that it's made of. It's going to stay that way, okay, until I actually do it myself and bend it over back to its original shape. But a paper clip is an example of plastic deformation. The yield strength is the point where it goes from elastic to plastic deformation. And we'll look at that at the in the stress-strain curve. We'll look at that in a minute. But just remember that the yield strength is the point where it goes from elastic to plastic. The next definition is brittle. Something that is brittle is when stress causes brittle materials to shatter into pieces. Okay, so meaning various different examples such as glass, ceramic, and peanut brittle. So stress can cause a lot of brittle materials to break and shatter into pieces. Okay, so it's kind of like they're fragile. Ductile is when stress causes That's a mistake. Let me go ahead and fix that. When stress causes ductile materials to stretch into thin wires or spread into flat surfaces. So basically, chewing gum, modeling clay, copper, and aluminum. So if you think about it, if I were to take a piece of aluminum foil and I applied some pressure on it, all it does is just flattens out even more. Or even if I take a piece of chewing gum or Play-Doh and I apply some pressure on it, all it's going to do is just going to flatten and spread into a flat plate, or in other situations into thin wires. So those are some examples of ductile materials. So we're looking at a stress-strain curve here. Okay, so there's a lot going on with this curve. So remember that, first of all, this right here where it stops, that's called the fracture point or the break point. Okay, so just remember that when it's the point at where it stops, that's where the material basically breaks. Okay, that's where it breaks. Remember from the definition that the linear curve is where elastic deformation happens. Okay? This is where elastic deformation is occurring. Remember, the linear part is elastic deformation. Plastic deformation is anything that is non-linear. So around this situation right here, all of this is plastic deformation because it's non-linear. Right here, where it goes from linear to non-linear, this is what we call the yield strength. And remember, the definition of yield strength is basically the point at which it goes from elastic meaning linear, to plastic meaning non-linear. So this would be our yield strength. And I want you to notice one thing here. It says Young's modulus is equal to rise over run. So I want you to make kind of a conclusion. Rise represents the y-axis. And what's on the y-axis? Stress. Okay, stress is on the y-axis. Over run. Well, run, what's on the x-axis? Strain. So so in a minute, we're going to introduce a new formula that's going to include that. Stress over strain. Stress over strain. So let's talk about that. The elastic region, before we do that though, I want to discuss the elastic region, and it's the region over which the stress-strain curve is linear. So if we go look at our stress-strain curve right here, this part here is the elastic region because this is the linear part. And then going back to the conclusion that we made between slope, which is rise over run, we said it was stress over strain. Okay? Stress being represented by the Greek letter sigma, strain being represented by the Greek letter epsilon. And this is going to be Young's modulus. Basically, Young's modulus is the slope of stress and strain curve in the elastic region. This value is represented by a capital E, and its units are in Pascal or PA, Pascal. Okay, so at this point you have an activity. These are the instructions in the activity. I hope that you are able to follow them along. Mr. O'Keefe will have the worksheet. I will go ahead and split you up into teams. I think 3 or 4 per person to a team. So I will let him know who the team members are. And once you're done with the activity, make sure that you turn in the standing worksheet, the standing strong worksheet into him. I just need 1 per group. You don't need, each one doesn't need to do it. But you do need to participate in the activity. Hopefully some of y'all can take pictures on your phone so that we can kind of share what the results were and who the winners were for this activity. If you have any questions, please let Mr. O'Keefe know. He has access to my contact information and can definitely call me if there are any questions or concerns. Other than that, I hope you kind of got a better idea as to what these definitions are, and I will see you on Tuesday. And remember that you do have a quiz, a vocabulary quiz over these terms on Tuesday. Also, before I forget, on Tuesday I'm going to also go ahead and make it a review day as well as a work on your project day, since your project is due next week. So if you have a laptop that you need to bring to work on your project with, any materials, any supplies, Tuesday will be the day where you will basically have a project day and work on your review for the vocabulary quiz, and then work on your quiz after that. Alright, I hope you guys have a good weekend, and I will see you next week.